Okay, in this video then we're going to take a look at another example of using the dynamic programming to come up with an optimum scheme for going from one condition to another condition. In this particular problem, we are generating, as a byproduct of cheese manufacturing whey, and it contains, among other constituents, protein and lactose. And so what actually happens in order to separate the protein, we go through a ultrafiltration process. And in that ultrafiltration process, the separation occurs based on molecular size and shape. And so a series of ultrafilters is employed, and in this case we have 4 stages of these ultrafilters to separate the protein and the lactose progressively. And we have, based on the incoming and the outgoing percentage of protein, that particular stage has a cost associated with it. And so that cost will be given to us in the next table. And we want to use then dynamic programming to solve for the concentrations that are leaving each of the stages. And so we start over here on the left at state 1 or station 1, and we go in with feed that's at 0.6% protein. And we run it through the first stage, and it comes out with a certain percentage of protein. That then is the input for the second stage. That comes out with a certain percentage of protein, and that goes into the third stage, and so on and so on. And finally, what you have coming out is 6% protein. And so in our particular process here, we're looking for the minimum total cost required to purchase these 4 filters such that the 0.6% protein is turned into 6% protein. And so again, in this particular case, they give you the example and the answer, and we're going to just see how that's done. This is, again, the chain associated with the feed coming in and then going out. And so this is the important table then. And what this table tells us is the operating cost of one stage of the separator, of the protein lactose separator system. And so what you have here is, depending on the entering protein concentration, which is along this axis here, which is the y-axis, when we come in, obviously, when we come in at 0.6 to a stage, there's a cost then, an operating cost, for converting that flow into a higher percentage protein. And the higher percentage proteins that one can affect is 0.9, 1.2, 1.8, all the way up to 6. And so if one was to just use a single separator coming in at 0.6 and coming out at 6, the cost would be 49.5. Okay, but in our particular case, we have the possibility of setting up 4 of these separators and determining is there a minimum cost that we can affect by utilizing less expensive separators in a string. And so this table then will allow us to obtain all of the various costs. So obviously, the first stage is going to be coming in at 0.6 and coming out at one of these 10 different possibilities with a cost associated. But then once we come out with a given percentage, the next stage, as you can see, if I went through and came out at 1.8, the next stage then would be coming in at 1.8, and then there's only a set of 7 possible outputs as we increase the protein concentration. And those 7 different outcomes then have a cost associated with them, and then we go to the third stage and so on. And so again, these are the dollars to operate one stage. And so as we look at this process, we again kind of go backwards. And we basically say, what if we look at stage 4 right here, and we say that it's coming out at 6%. What must it have to come in at? And what's the cost of this stage 4? So just like before, we are looking backwards, and we're saying that it's coming out at 6, but it came in at one of these other numbers. And so this table here then shows that if we come out at 6, but we went in at 5.4, it cost us 126. So let's see where that's at the table. At the table, that's this value right here. We come out at 6, we go in at 5.4. And so this runs all the way up to 1.8. Now, why only 1.8? Well, one of the constraints in this particular problem is that one has to use all 4 separators. And so that last stage is the only possibility of coming in to that last stage is 1.8 if the other 3 stages are just taking it 0.6 to 0.9, 0.9 to 1.2, and 1.2 to 1.8. And so that's why the table only includes up to the 1.8. So that's our first round of stage 4. And so again, once we get to the input to stage 4, there's only one path and one cost. And so then we can go and we now can look at a new table. And now this new table is going to look at what is the concentration coming in at stage 3. And so if the concentration coming in at stage 3 is 1.2, and if we allow it to come out at 1.8, there's a cost associated with that. And again, we could go back here, and if it comes in at 1.8 and comes out at 1.8 and comes 1.8 and comes out at 2.4, the cost is 374. And so, 554. Let me do, okay, 554. Right here, I'm sorry. We came in at 1.2 and we came out at 1.8. It's 554. And so that's this. We came in at 1.2, we come out at 1.8, the cost is this. And so what we have in this first group of the table is coming in at 1.2 and going to this value, we have that cost involved. And now once that is the cost for stage 3, there's only one path to go from that, and that is the values that we've already determined if we enter stage 4 at this value here. And so by doing this, we then see that if we come in at 3 with a 1.2, there is an optimum, a lower value associated with the path to go from there. And so if we come in at 1.2, we need to then allow that stage to go to 2.4, and then from 2.4 to 6, and that gives us the minimum amount of cost. And we could do that then, assuming that we come in at state 3 at 1.8, and now we only have 6 possibilities, and those 6 possibilities are to go to 2.4, and the cost is 374. Again, going to the table before, coming in to a given stage at 1.8, going to the new value, and then once we get to the new value, there's only one cost that is going to be from that value, and we see 1567, and we then repeat those same values less the first one. And so by doing this, then we see that we add the two together, and we see if we come into stage 3 with 1.8, we actually then have a minimum that's 18.12. Likewise, we continue to do the process with 2.4, and we look at the combinations. This time there's only 5 combinations. Those 5 combinations, once we arrive there in stage 4, there's only a given cost to get to the 6%, and we add those together, and we have now a minimum of 1288. We do it for 3. We have 4 possibilities. We have a minimum of 9.25. We come in at 3.6. We have a minimum of 657. These minimums are going down, obviously, but if you look at what's actually happening, we have performed more of the we've increased the concentration, leaving less concentration to be increased for stage 3 and 4. And so even though 26 and 18 and 12 and 9 and 6 and 4 and 2 are much lower numbers, that's going to be compensated for by higher dollar amounts of the stage 1 and stage 2. So we filled out this table here, gets us through state 3. Okay, now the important thing about this is once we now go to state 2, and we go through state 2 to state 3, whatever we enter, whatever we get for the output of state 2 is the input to state 3. We only have one path to go from that point. We don't have to do all of the additional combinations. We already know halfway through the process how to finish up the process. What is the best path to finish up the process? And so this table then has us coming in with a concentration entering the second stage. Now the lowest one would be 0.9, assuming that the first stage brought it from 0.6 to 0.9. And 0.9 can go to 7 separate values. And again, that concentration increase here costs this amount from the table. But then once we get to this point right here, we go to the previous table to go and get the optimum value. And we add that optimum value to the cost of the second stage, and that gives us then a optimum total for those 3 stages. And so if we come into stage 2 with 0.9, we see that the minimum cost is going to be $28.89. If we come in with 1.2 and look at the combinations and then put in the values associated with that going from that point through the other 2 stages, we get a optimum that corresponds to either of these 2. And then again, 1.8 going to the 5 separate possibilities. We have a cost associated, we have the optimum, and we have the 1658. And again, we can continue that process, finding an optimum at each particular location. Again, these numbers are getting smaller, but it just means that that first stage has to do quite a bit of work to get it up to this. And so that extra amount of work is going to be required in the next table. So even though these numbers seem low, as opposed to this, we still have a lot to do, even though 3 stages have been optimized. And then finally, we back up until we look at just the first stage. And now the first stage comes in at 0.6. There's only one entrance to the first stage. And if we go just up to 0.9, we see that the cost is this 553. If we went all the way up to 4.2, we see a very large cost associated with bringing it up to 4.2. And then 4.2 then has an optimum from that point. Now, you'll notice that 4.2 coming into state 2, 4.2 was the highest that it can come in, again, because of the constraint that we have 3 more separators. And so we can't come into 2 with anything higher than 4.2 because we have to have a separator 3 and a separator 4. And so the same thing happens on the other end that we saw. And so now when we bring coming in at 0.6 through these values, putting in the values from the table and putting in the optimizations, we then find that the optimized cost corresponds to 34.42. And that's our optimized cost. Almost this case right here was almost as good, but this would be the one that we selected. So we can now back up and say, what is the solution? What's the optimized cost? The optimized cost is 34.42, starting at 0.6, going to 0.9. If I went back, as I said, we had the answer, and the answer was 34.42 going. The first stage was from 0.6 to 0.9, and then we saw that the optimum coming from 0.9 on the second stage was to go to 1.8, and that was to go then in the third stage to 3.6, followed then by 3.6 to 6.0. And so again, this dynamic programming calculation, typically you work your way backwards and you determine by going through the last stage, you figure out what the optimum is, and then you back up and look at the combinations there. And once you reach a particular stage, you then, going forward, you already know what the optimum is. And so again, an example of using the table and going through additional tables to find the optimums as you go, instead of trying every combination every time. Okay, so this particular problem I just added in here, and again, it's a minimum cost pipeline to be constructed between positions A and G, very much like we had before. And it can pass through any of the 6 locations, B, C, D, E, and F. Okay, so had this been a problem, one would have had a table for the cost associated with going from A to any of the 6 Bs, and then from Bs to Cs, there would be a cost associated with those, and so on and so on and so on. And all that is being asked for in this particular problem is you have the 6 of these intermediates, you have a beginning and an end, and you have 5 of those substations. And so the question posed is, if all possible combinations of routes are investigated, how many different paths must be examined? And so again, that would be if you brute force the problem. You know, if you went through, so try to figure out how many different combinations you would have to go through. And now, if dynamic programming is used, how many calculations must be made if one calculations consist of one line in a table. And so now we can go back and we can say, computationally, how much did we save in using this programming technique? And so I would like for you just to kind of think about that. If we were doing dynamic program, what we saw was working our way backwards. We saw that there were 6 separate calculations or 6 lines associated with going from F to G. And then when we started at a given point here, we looked at, okay, this had to go to 6 different possibilities. And then this one had to go to 6 different possibilities. This had to go to 6 different possibilities. This had to go to 6 different possibilities, so on, so on. So from E over, we see that there is 6 times 6. Okay. Well, we had this, 6, and we have 6. That's 36 plus another 6, which is 42. But the result of doing that gives us then just 6 pass from this point on. And now we're ready to come up here, and we recognize that there is, as we go over from this point here, we have 6 possibilities. Okay, we have 6 possibilities here, 6 possibilities here, 6 possibilities here, 6 possibilities here, 6 possibilities here. But then that's 36 more possibilities. But then once we get through that, we then have only 6 pass from that point on. And so you can kind of go through and see how this adds up, as opposed to starting from here and saying, okay, I'm going up to here and I'm going to every one of these 6 here. And then I'm going, for each one of these, I'm going to every 6 possibilities here, every 6 possibilities here, every 6 possibilities here, 6 possibilities here, and or 1 possibility. And so when you go through this way, and then you have to go, then you basically have 6 times that as you go through the process again, and you'll be able to compare the differences in the accumulation of pass to see that just a brute force means is much more costly than using this dynamic programming. Okay, so we're going to stop at this point, and the next lecture, the next video, will then cover our last problem, and that problem will be the one that we will have due as a homework problem for this particular section.